We are continuing with Unit 9, Parametric Polar and Vector Equations. Today is Lesson 6, Area in Polar Curves. So students will be able to graph polar equations on a polar coordinate system and determine their area. So we are going back to, remember these, where we had a function, we had f of x, and we went from A to B, and we were finding this area in here. Remember these? And we said that the integral was, the area was equal to the integral from A to B of f of x dx. And if we had a curve on the bottom, we would subtract it, f of x minus g of x. And I had these funny looking little figures in here, my stick figures, where I said head minus feet. We're still doing that, but now we are in polar coordinates. So what you have to imagine is this whole x-axis being shrunk down into one point that you're kind of pinching it together. And if you pinch it together, this outer piece, this red line, is this red line here. And then all the feet are down here at the origin. So it's kind of like our 2 feet are together. So there's my stick figure. It's still head minus feet, but all the feet are pinched together at the origin. And what we have is our area formula is 1/2, don't forget that 1/2, alpha to beta, that's in place of A to B, f of theta, because we're in polar coordinates instead of rectangular, d theta. So this is very similar to area is equal to pi r squared. Now I have this 1/2 in the front as well. That has to do with circles and all that other stuff, but we'll figure this out. Example 1, find the area of a right semicircle r equals 4 sine theta, radius of 2, tangent to the x-axis at the origin. Now this is a straightforward one. We really should be able to know what this looks like. I'll pop into my calculator in just a moment, but if this is my xy plane, we have a semicircle r equals 4 sine theta. If you have sine, that actually aligns on your y-axis. So there's my circle. 4 is the distance all the way up to here. 4. Radius of 2, so 2 kind of happens in the middle. Tangent to the x-axis, so we're definitely tangent to the x-axis, and we're passing through the origin. Now it says semicircle. So this is the semicircle piece that we're talking about, a right semicircle. So we're only in that first quadrant. Now I'm going to pause the video here for a quick second and show you my calculator. All right, so I'm in my calculator now. R1 equals 4 sine theta, and I just want to show you the graph. So there it is. I can probably zoom out a little bit. Zoom out. There we go. So there's the circle. It is kind of sitting on the y-axis and is tangent to the x-axis. And we have a diameter 4 and a radius of 2. So there we go. So let's go back to our problem. All right, so our equation, I'm going to grab it from up above. Area is equal to 1/2 alpha to beta, that's A and B, f of theta quantity squared d theta. So A is 1/2. I'm going to come back to alpha and beta in just a minute. F of theta, that's your function with respect to theta there, is 4 sine theta. So 4 sine theta quantity squared d theta. Now, alpha and beta, you have to imagine that you're standing right here at the origin, and you start by facing over here at 0, just like the unit circle. And then you're kind of a spotlight or a searchlight, and you're rotating up, 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 up until you hit the top. So our gut, from what we've done in geometry and algebra and calculus before, wants us to think that, oh my goodness, we're going to go from, because it's half of a circle, right? That you're going to go from 0 to pi. If you're going halfway around a circle, it's 0 to pi. Yes, but no, not in this case. We're starting here at 0 and we're going to go up and stop here. This is pi over 2. If we went to pi, that would actually be the whole circle, and 3 pi over 2 would be down here on the bottom. So your alpha and your beta, takes a little while to convince yourself of this, is 0 to pi over 2. 0, here's my 0, up to pi over 2. I know that feels a little weird. I know some of you are not going to like that at all. Now, it is possible to do this by hand. You can also do it in your calculator. This is 1/2 0 to pi over 2. This becomes 16 sine squared theta d theta. Your 16 can come to the front. It's not necessary inside of your integral. 1/2 times 16, 0 to pi over 2, sine squared theta d theta. Now, sine squared theta you can replace with a Pythagorean trig identity to be 1 minus cosine squared, but that doesn't actually do much for us. So somewhere in our notes, I don't remember where, there is the integral formula for this. And this is one that you should have memorized. I always have to look it up because I don't want to get the signs wrong, but this is what it looks like. Theta over 2 minus sine theta cosine theta over 2. It is one of those angle identities, half angle identity, I think. And then if you integrate that, but that's what it turns out to be. So we have, how do I want to do this? Leave the 8 on the outside. This is pi over 4 minus, if I put a pi over 2 in for cosine, that's 0. So that's kind of handy. And then if I put in 0, well, this is 0. Oops. I don't care about stocks. Slip of the hand and notability here. 0, and then sine of 0 is 0. So this is 0. So we are left with 2 pi. Now, if I stop sharing my screen here, let's hop over to the calculator. All right, so in our calculator, let's get away from our graph. Let's do math 9. I want to integrate from 0 to pi over 2. And inside here, I'm going to have, I'm going to do my parentheses, 4 sine theta. Close this, square it. So I know it looks like the theta is being squared, but in calculator world, actually, that's just the sine being squared, not the 4. I need to close my parentheses again. Hold, please. There we go. Now I want to square this. Square this. So that squares the entire quantity. And then d theta. And don't forget, I have the 1/2 in the front. So I'm going to divide this by 2. I could multiply by 1/2 and got the same thing. So 6.28. So 6.28 kind of sounds like 2 times 3.14, doesn't it? Yeah, that's 2 pi. Same thing. All right, we got it. All right, next up, we are going to sketch r equals sine 3 theta and compute the area of one petal. Now, could I put this in my calculator? Yes, but should I know how to do this by hand? Yeah, I probably should. So I'm going to start with a theta radius table, and I am going to choose some values. So what values do I choose? Well, that 3 is going to be kind of handy. So I'm going to make sure I'm using ones that when I multiply by 3, I get a nice value that would still be on the unit circle. So I'm going to choose 0, pi over 6. I'm going to skip over the pi over 4, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and then pi. Now, if I take each of those values and put them into sine of 3 theta, well, sine of 0 is 0. 3 times pi over 6 is pi over 2, so sine of pi over 2 is 1. Pi over 3 times 3 is just pi. Sine of pi is 0. Pi over 2 times 3 would be sine of 3 pi over 2. That's a -1. 2 pi over 3 times 3 is 2 pi. Sine of 2 pi is 0. 5 pi over 6 times 3 is 5 pi over, gotta think about this, 2. This would be a 1 if I keep going around my unit circle. And then sine of 3 pi would be 0. So I have zeros, ones, and -1. So let's try to graph this thing. So I am going to give myself something to work with here. I'm going to choose, I'm just doing 1 and -1. I'm going to pick this ring as my radius of 1. I don't want it to be all the way out to the edge in case I have to go beyond it, but I'm going to choose that for my radius of 1. Now, when I plot points, theta 0, radius 0 here. Theta is pi over 6, radius is 1. So here's pi over 6, radius is 1. I'm right here. Pi over 3, I'm at 0. Pi over 2, so I'm facing up, but then my radius is -1. I'm actually down here. And then at 2 pi over 3, so 2 pi over 3 is over here. My radius is 0 again. And then at 5 pi over 6, here's 5 pi over 6. My radius is 1. All right, so what does this look like? Well, you want to sketch this in. Let's go for a highlighter. So 0, 0, pi over 6, 1. It's not going to be in and out and in and out and in and out. Remember, these are polar. They're loopy. They're smooth curves. So 0, my radius of 1, back through 0. I had a radius of -1, back through 0, a radius of 1. And then at pi, we're back down here at 0. So even though we're only sketching between 0 and pi, you actually get that full picture with the negative radius. So let's do some calculus. You can confirm that in your calculator. That's exactly what it would look like. So area is 1/2 alpha to beta, your function, your radius squared d theta. So 1/2. Now, the area of one petal, that's going to come from our boundaries. We'll come back to that in a moment. Sine of 3 theta quantity squared d theta. Here are my boundaries. So one petal, that's all we're looking for. One petal. So what do I use for boundaries to get one petal? You're going to go from 0 to 0. And it technically doesn't matter which one you use because that's where it kind of pinches off one petal. Radius of 0, radius of 1, back to radius of 0. I kind of like the earlier ones where we can use the 0, but technically you could use any of them that go from 0 to 0. So I'm going to choose my boundaries as 0 and pi over 3. Okay, awesome. So what's next? Well, to do this by hand is some U substitution, believe it or not. It's been a while since we've done that, so let's jump in. U is equal to 3 theta. Du would be 3 d theta, so I'm going to pop into 3 and a 1/3. And when I do that, I've got 1/6, 0 to pi over 3. This is sine of u quantity squared d theta. There's still that 3 out there. Let's scroll down here a little bit. 1/6. Now, this is really sine squared of u, and just like we had up here in this example, I'm going to use that same integral rule to do this by hand. So I've got u over 2 minus sine u, cosine u over 2 between 0 and pi over, I have to change my boundaries, don't I? If I'm in u, this is not pi over 3 anymore. This should just be pi. Good, 0 to pi. All right. Now, if I substitute in my pi, this is 1/6 pi over 2. Sine of pi is going to be 0, so this is 0. And if I substitute the 0 conveniently, this is 0 again. Sine of 0 is 0, so this is 0. So we are left with pi over 12. If you jump into your calculator and do math 9, you should get the same thing. Hold that thought. All right, so I've already put example number 2 into my math 9. I'm going to hit enter. I have 0.523, but I didn't do the 1/2 in the front. So last time I divided by 2, this time I'll multiply by 1/2, or it could have been 0.5, doesn't matter. And you get 0.261. Now, we had said our answer was pi divided by 2, so let's see, pi divided by 2. Not pi divided by 2, how about pi divided by 12? Try again. There we go, 0.261, 0.261. So we do have the right answer. Excellent. All right, last thing, area between two curves. So back when we were doing area in the rectangular coordinate plane, we could have had this f of x, and then down below we had g of x, and here's my b, over here's my a. If we were looking for this area in between, and I know I mentioned this already, the area went from a to b, f of x minus g of x dx. And I had my crazy stick figures. I know they were cheesy, but you had the tall friend and then you had the shorter friend and you subtracted the two. The same thing is happening here. Here's my tall friend, the outside radius. And then there's a shorter friend, which is the inside radius. It's weird because everybody's feet are together. But it's still, instead of top minus bottom, this is now outside minus the inside, outside minus inside. So what I have for you is example 3. We're going to give this a try. Find the area inside r equals 2 cosine theta, but outside of r equals 1. So the first thing that you want to do is get yourself a picture of this. Now, can you put this in your calculator? Yeah, you absolutely can. It would be helpful if you had, an idea of what this looked like. Let's start with radius equals 1. Make that one blue. Radius equals 1. Now, I'm not going to go all the way up to the outside. I'm going to choose 1, 2, 3, 4. I'm going to choose my 4th ring as 1. That's my radius of 1. So then I'm counting by 0.25. Okay. And then we have 2 cosine theta. So 2 cosine theta, I know that's a circle that sits along the x-axis. R equals 2 cosine theta sits on x-axis. It would be tangent to the y-axis. This is kind of your diameter. Not kind of, it is your diameter. Choose your diameter. So the radius is 1. So this circle has a radius of 1. And I counted those as 4. So 1, 2, 3, 4 gets me out here to 2. So it's a circle that looks like this. It'd be the same size as the blue one. I didn't really do a great job of showing that, but there it is. So where am I trying to find this area? We are looking to be in the side of 2 cosine theta, but outside of r equals 1. So there's 3 possibilities here. We're actually looking for the one furthest to the right. We're looking for this area out here. Okay, so just like we did in rectangular coordinates, if we have 2 circles that intersect one another, or 2 figures that intersect, we want to set them equal to each other. So I'm going to say that 2 cosine theta is equal to 1 cosine theta equals 1/2. Think of your unit circle. Where does that happen? That happens at pi over 3, and it happens at, go all the way around, all the way down here, 5 pi over 3. But I have an issue with that. Pi over 3 is over here. My circles are a little bit short. So it intersects at pi over 3. And yes, indeed, this down here is 5 pi over 3. I know I missed my points a little bit, but that's okay, 5 pi over 3. However, if I go from pi over 3 to 5 pi over 3, that's really finding the area over here. And that would find the area inside the blue, but outside of the red. Not what I'm looking for. I want what's on the right-hand side. So you have to think to yourself, especially down there in that fourth quadrant, things get a little crazy. What's another name for 5 pi over 3? Well, the negative spot is negative pi over 3. And that's actually the name of it that we want. So we're going to use negative pi over 3. So when you find the area here, now you're going from negative pi over 3 to positive pi over 3. And that's giving you the right-hand side of the circle, which is exactly what we want over here. So to set up the integral, the area is 1/2 negative pi over 3 to positive pi over 3. You want the outside radius, which is the red one, 2 cosine theta, quantity squared, minus what's the inside radius? The inside radius is a 1. I guess I had the other blue. 1 squared d theta. If we go to clean this up a little bit, area is 1/2 negative pi over 3, positive pi over 3, 4 cosine squared theta minus 1 d theta. You can actually go through and do this as 2 separate integrals. There's a couple things that you can do here. I have a whole page worth of work to get you there. What can I do? I guess I can upload that. You know what else I can do? I can share it with you so you can take a screenshot, but the answer is going to be pi over 3 plus root 3 over 2. That's the area. Now, I want to show you one other thing before I show you all the work that got you there. And again, Math 9 in your calculator would do that as well. Depending on the problem, and I know this used to happen in our old textbook a lot. Yes, you could use the 2 points of intersection, but in polar graphs, a lot of times they're very symmetric. So instead of going from negative pi over 3 to pi over 3, what you could actually do is go from 0 to pi over 3. 2 cosine theta quantity squared minus 1 squared d theta. And this would be 1/2. So if you're only going from 0 to pi over 3, now you have to double. And conveniently, that 2 times 1/2 cancels out, which kind of works out kind of nice. And then you have a 0 to substitute into your problem instead of a pi over 3. So just keep in mind, there's another way to look at this. Now, if you're interested, I'm going to switch screens so that you can see my handwritten work on the other one. All right, don't mind my messy handwriting. This is a screenshot of, or a PDF of my old notes. So there's the figure that we just drew. Here is my negative pi over 3 to pi over 3, 4 cosine squared theta minus 1 with the 1/2 in the front. And then what I did was, what did I do? I used a trig identity in there with that cosine squared and the cosine of 2 theta, double angle identity. And then I broke it into 3 pieces. I did some distributing, and then I combined like terms. And then to integrate 1, that becomes a theta. To integrate cosine of 2 theta, that's sine of 2 theta divided by 2. And then I put in my boundaries of negative pi over 3 and positive pi over 3 and evaluated those on the unit circle. And that's where I'm coming up with the pi over 3 plus root 3 over 2. So that's probably a little bit of extra work in the than the AP exam would ask you to do, but I did want you to see those. So you can go back and take a screenshot of those if you want to. Good luck. I kind of like polar area. I love calculus because it's algebra and it's geometry and it's everything that gets crashed together. But this particular unit is polar and it's calculus and it's geometry and it all crashes together. So let me know if you're stuck anywhere.